Hey, PChem, I just want to give you a little bit of help, a little bit of pointers as we start to look at the mathematics on this Iodine Clock Lab. Results were looking really, really good. I was excited how clean and how consistent our results were coming out. But today we're spending some time kind of crunching some of the numbers, making sure we got those calculations squared away. So if we're following on down, sorry. We ran a bunch of trials, we collected a bunch of data. All of that data is available on that Google spreadsheet. We need to do for our lab, for our calculations, we need to show our work for any of these shaded values on our data table. The good news is average time, bloop, that's from the spreadsheet. Cool, great. Now we need to figure out what our molarities are at that initial start of the reaction. And for that, we got to do a little bit of work because right when you dump everything together, we've diluted our solution. If we think about, so we had some starting concentration, for example, of our iodide ions. I think that came from the potassium iodide. The potassium is a spectator. Really, it's just that iodide ion that we're interested in. It was a certain concentration. Let's scroll back up for just a second. We know for solution A with our potassium iodide that when we first dumped it in, it was 0.200 molar. That was its concentration for what we measured out for that particular trial. And then it got diluted because we added some of B and some of C and some of D. So we got to do a little bit of work. Good news, it's all about molarity. Big M is molarity. Remember for your formula that molarity is moles over liters. So we can actually calculate how many particles are floating around. So we need to do a little work. We know that for reaction one, let me get to the right table here real quick. So if we're going to try to figure out for reaction one, what our new concentration of iodide is, could we do it? Well, sure. We know that originally for this potassium iodide, it was 0.200 molar, and that just equals the moles over our liters. Well, okay. I'm going to do for mixture one, just to show you an example here. For mixture one, we measured out 20 mils of solution A. Well, if we know the volume, we know the molarity, we can solve for the moles. And those moles are going to stay the same no matter how much you dilute by. And so we can go ahead and plug in what we know. We know for that first reaction, 0.200 molar. That's going to equal some amount of moles over in liters, 0.020 liters. Okay, to solve for X, we would multiply. We would take 0.2 times 0.02. And we find that for that first trial for the iodide ion, the potassium iodide, we measured out 0.0040, sig fig check. It's like 3 sig figs, 0 moles of our Ki or our I in this case, which is the part we're interested in. Cool. Now, question, what did we do with these moles? Well, we diluted them. We put them into a new total volume. And here's the deal. It seems silly we did solution D, right? It didn't react with anything. The potassium was floating around, the chloride was floating around. What did that solution D do for us? Well, if we look at solution D and our mixture one, in mixture one, we didn't need it. But if you add up all your total volumes for that first reaction, 20 plus 10 plus 20, you'll find that the final total volume is 50 mils. Here's why solution D is so important. If you do the same for mixture two, 15 plus 10 plus 20 plus 5, it is 50 mils. Because we added solution D, all of our new total volumes are going to be 50 milliliters. So if we want to know what our new total concentration is, we take our total moles of substance in solution. We know we added 0.00400 moles of potassium iodide. We are going to divide that by the new volume. In liter form, that's 0.0500 liters. We divide those and we get a new starting concentration once everything's been diluted, 0.0800 molar for our iodide solution for I minus. So we gotta go through, do a little bit of work, figure out what all the new concentrations are right when we add them all together. And these will be the initial concentrations we'll use for all of our trials. Cool. If we take a look then at our additional calculations, once we got these molarities, I think we're kind of off and running because now we've got a way to calculate our change in concentration over change in time. Well, S2O3, that's this column, will have that value from our calculations, from our molarity calculations. It's -1/2 because of our balanced chemical equation. For our rate expression, we use our coefficients. Well, it's a 2 here. It's negative because it's getting used up. It's a reactant. And so technically, if we were doing the change in that substance, well, it's our limiting reaction. It's all getting used up. So final would be 0 minus this value gives us a negative number. This negative in front cancels with the negative here to give us a positive value. The 1/2 comes from the coefficients. Then we just need the change in time. Well, the change in time is the average time for mixture 1. And that will give us our expression or our concentration, change in concentration over change in time for mixture 1. Cool. Hopefully this helps you get started on some of the calculations. If you have additional questions, do not hesitate to reach out. Do your best. Come on back with questions next time I see you.